Welcome, ladies and gentlemen. May I have your attention, please? Thank you. So let's go ahead and take a look at our Bellwork today. Last class, we developed the trapezoidal rule as a means for approximating the area underneath an irregularly shaped curve. And today we're going to continue that notion of using shapes that we do have an area formula for to get better and better approximations for the area underneath irregularly shaped curves. So let's take a look at Jack's velocity as he walks his dog. When is Jack slowing down? Well, we can apply what we already know about rectilinear motion back from our investigations in Unit 3. When velocity and acceleration have the same sign, then we know that Jack would be speeding up. When velocity and acceleration have the opposite sign, then we know that Jack would be slowing down. And so it appears as though for the entire duration of this graph, velocity is positive. Therefore, velocity and acceleration would only have negative signs when the derivative of velocity, the acceleration, was negative. And so we're looking for decreasing behavior on positive velocity, and that occurs right over here. And so it appears as though just in this time interval here from looks like t equals 12 to t equals 16, that's when we expect Jack to be slowing down. And so if we express that with interval notation, we could say from time t equals 12 to 16. I would ask you to raise your hand if you had that, but I can't see you right now. Let's consider the next one. So let's approximate, let's see, t sub 4 means. So this is our notation for a trapezoidal approximation with 4 equal subintervals using 4 trapezoids. And so this means that we're going to use 4 trapezoids in our area approximation. All right, so let's go ahead and see if we can use the data in our graph. I'm thinking Warrior Pride. Let's see if we can use the data in our graph to figure out an approximation for the area underneath that irregularly shaped region. So let's see. Delta x, that's my step, each subinterval given by delta x. And if I have an entire interval that ranges from 0 to 16 seconds, that is the length of the interval, b minus a. And if I could divide that by the number of trapezoids that we're going to do, and so divided by 4, then we could get our delta x. And so it looks to me like 16 minus 0 is the length of my interval, and we know that we want that all over 4 trapezoids, looks like. So it looks like the width of each subinterval then is going to be 4 units. And so let's go ahead and break it up into our 1, 2, 3, 4 trapezoids. And we can do that by partitioning our entire interval, 0 to 16, into 4 equal subintervals. And then we'll go ahead and use the trapezoid as our shape to approximate that area. So we'll go ahead and draw some trapezoids here, connecting the function values on the endpoints of each subinterval. And we see our trapezoids there do a fairly good job of filling up that curve. And we now can get an approximation for the area underneath the red curve, Jack's velocity graph, by using the function values provided from these points. And so I know that t sub 4 is given by, let's see, delta x is 4 divided by 2. There's my 1/2 for my trapezoid formula. And then we want our first function value. Looks like our first function value right here would be given by 5. Plus we want 2 of that second function value because that 7 acts as the base in this first trapezoid as well as the left base here in the second trapezoid. And so we need that 7 twice. And so we'll go ahead and do 2 times the 7. And we need 2 of the 12. And we need 2 of the 15. And lastly, just 1 of the 13. That function value only acts as the base of the rightmost trapezoid. So we only want to count it once. Okay, so if we work this out now, we've got our delta x divided by 2. We've got our first function value, 2 of our next function value, 2 of our next, and so on up until 1 of the last. And we can go ahead and do our calculation. It looks as though we've got 5, 2, 14. Carry the 9, square root of the inverse tangent. 86, you have to check my math on that, Riley. We need 86, and so it looks like, go gadget arm, looks like we're at 172. And to get a label on that, we can always consider our y units. Let's get that bigger. Our y units times our x-axis units. That is feet per second times seconds would be feet. And so it looks like here we've got feet for our label, and that makes sense. The distance that Jack traveled during his walk is approximately 172 feet. Great. And so the final portion there. For what time values is my approximation underestimate versus an overestimate, and why? Well, if we think back to the shape of our trapezoid, it appears as though my trapezoid lay above the red curve over this first time interval. During this next time interval, it was a little above, I would say. And then I would say below, definitely lay below the red function values for those last 2 subintervals. And so I'm thinking that when my trapezoid lies above the curve, it's giving an overestimate, versus when it's beneath the curve, it's giving an underestimate. So we could say an underestimate for, let's do nothing like stars. So we'll do an underestimate on the time interval 8 to 12, how about? So we'll go 8 to 12. And also 12 to 16. Okay, and if we thought stars were neat, what about happy faces? I'm thinking overestimate, an overestimate. Looks like an overestimate on 0 to 4. And 4 to 8. Okay, excellent. So let's go ahead and at this time take out your OTL number 2. If you could make sure that your heading, name, first and last, hour, and OTL number 2 are clearly labeled. Give yourself credit for those 2 problems from last night in pencil. Divide by 2, enter. That's an exercise in patience. Times by 2, and let's box that Infinite Campus score nice and big. Round to the nearest half point, 0 to 2. And we can go ahead and pause the recording and make sure you have an opportunity to collect that. Thank you. Okay, ladies and gentlemen, at this time we should have collected our OTL number 2. And we're going to take a look at how a trapezoidal approximation can be used to get an approximation for the area underneath an irregular shaped curve. And so once again, we could generate delta x, that is the width of each subinterval, by considering the length of the entire subinterval and then dividing by the number of trapezoids that I wish to use. So in this case, T sub 3 is asking for a trapezoidal approximation using 3 trapezoids. Again, we can do the length of my interval and then divided by the number of trapezoids that we're using, in this case 3. And so for us, it looks like 14 minus 2 is 12 divided by 3, so it looks like 4. if we partition our entire interval up into 4 equal subintervals, then we're going to go, I'm sorry, into 3 equal subintervals, each of length 4. Then we can go ahead and draw those in now. So from 2 to 6 is the first subinterval. 6 to 10 would be the next subinterval. And lastly, 10 to 14. And we'll get our trapezoids now by connecting the endpoints of each subinterval. And there we can see. So our trapezoids could be used to approximate the area underneath the curve. Here's our first one. Our second one. And our third one. And really this is more now about seeing what kind of tools we have to offer here in Smart Notebook. I'm at the other side. Okay, great. So not only can trapezoids be used, but it turns out that a much simpler shape can be used if we apply our concepts of calculus that we investigated earlier in the year to get a better and better approximation. So now we're going to go ahead and investigate Riemann sums and the definite integral in activity 5.4. We've got stamped eligible items in 6, 8, and 12E. If you take a minute and circle those stamped eligible items. To get your 6 and 8 stamps, which I'll do some next time, you want to make sure that you're keeping 3 decimal places and you're being careful with your accuracy and attending to precision. Your 12E stamp is very similar to our closure that will be coming back and rejoining after you guys work together in your cooperative learning groups. So once again, new seats, new cooperative learning groups. If we'll go ahead and pause the recording now, and if you could go ahead and scooch into your cooperative learning groups now, we'll rejoin, take a look at an upper lower sum, and then our closure. Thank you for getting started now. Okay, ladies and gentlemen, thank you for coming back together. Let's go ahead and take a look at our lower estimate using 6 rectangles for a Riemann sum as opposed to our upper estimate. Unlike right and left-hand sums, which always use the same side function value to generate the height of a particular rectangle on each subinterval, the lower sum always uses the least function value that's encountered over the course of each subinterval to generate the height of the rectangle for that subinterval. In contrast, an upper sum always takes the greatest function value encountered over the course of each subinterval and uses that as the height of the rectangle for the entire subinterval. And so just quickly, I want to make sure that you're comfortable with lower versus upper for our Riemann sums. A lower estimate using 6 rectangles. It looks like we can partition my entire interval 2 to 4 into 6 equal subintervals by doing 14 minus 2 is 12 divided by 6 is 2 units for each. So if we went ahead and broke up each subinterval as 2 units long, and we took our rectangle heights and based them on the least function value that's attained over the course of any in the interval. So it looks like for my first rectangle height from 2 to 4 for my x values would be given by this rectangle height because it's the least function value that's attained over the course of the entire subinterval. Similarly, this next subinterval from 4 to 6, it looks like the least function value attained is right there at the bottom of the dip. It's not coming from the left-hand side or the right-hand side of the endpoint of each subinterval. It's coming from the least function value attained. Here we go. Again, we're basing the height of my rectangle based on the lowest function value attained over the course of each subinterval. Replacing that as such. Looks like that. There we go. Now we'll go ahead and draw in our heights. I'm sorry, our sides of our rectangles. All right, let's go ahead and contrast that now with the upper estimate. And so for the upper estimate, now we're talking about the function values, the greatest function value attained on a given subinterval. That's going to be responsible for giving us the height of the rectangle over the course of that subinterval. So there we go. There's the highest function value on that first subinterval, 2 to 4. Looks like from 4 to 6, the greatest function value comes from there. on the left-hand side from 6 to 8 looks like the right side right here gives us the greatest function value attained over the course of the subinterval. This subinterval looks like right up there is the greatest function value attained. Looks like here. And then for this top one, remember the top, the greatest function value attained over each subinterval is responsible for creating the height of the rectangle for that subinterval. So we're not doing a right side endpoint or left side. It looks like the top of that function right there, that maximum is going to yield the result. And so I just want to make that clear. So we're using that topmost function value there. Great. Okay. And so then again, you could go ahead and take the time to do the sides of your trapezoids. In the interest of time, we'll go ahead and continue on. The key part was deciding where we're going to get our height of the rectangle from. In an upper estimate, we can see that the greatest function value is used to determine that. Okay. So we want PDFable, Kyle, so I'm going to go ahead and let's see. There we go. Much better. Okay, let's take a look at a final approximation, the midpoint Riemann sum. And you've seen midpoint in the past. And we just want to make sure that you're comfortable determining where it is that you're going to take the height of each rectangle from again. And so in this case, we're going to go to the middle of each subinterval. Again, my subintervals will be a length 2 units on the x-axis. And we're going to go up from the middle of each subinterval until we hit the function. That's going to determine what value I use for the height of a rectangle on each subinterval. And so if I could go in the exact middle of each of these subintervals and go straight up until I hit the function, that will be the height of the rectangle that we'll use. And so I'm trying to get in the middle of each of these subintervals with my mouse pointer at home. Doesn't help that the PDF is scanned in a little bit crooked, but all right, so let's go ahead and get the heights of those rectangles now with the super duper infinite cloner. Looks like there's my height. There's the height we're going to use, comes from the middle of each subinterval. There we go. I think you got all of them. Thank goodness for snap guides. Okay, I need all the help I can get. So let's go ahead and bring it back to closure now. So once again, I'll pause the recording so that you have an opportunity to complete the closure. When we come back together, we're going to determine what each of these pieces in this definition for our Riemann sum, what each of these pieces refer to. We'll go ahead and pause the recording, give you about 2 to 3 minutes to complete, and then we'll resume the recording. Okay, ladies and gentlemen, may I have your attention, please? Thank you. Let's go ahead and break down the pieces of this Riemann sum definition. What does n represent here? Well, n, just like t sub 3 from the beginning, or t sub 4 from the Bellwork question, that represents the number of rectangles that we're going to use. So n represents the number of rectangles. That we'll be using. What is that? So that's our Greek letter. That's a sigma. So what does that sigma notation tell us? Well, it means that we're going to be summing things up. Sigma summing things up. We'll be adding things together. So we'll be summing up. And not our lesson objectives like closure, but actually summing up these terms here. The terms f of c sub k times delta x sub k. So this product, f of c sub k times delta x sub k, represents the area of a typical rectangle. And in this case, the kth rectangle encountered on some interval a to b. And I think it's time for Warrior Pride again. Okay. So then what does the f of c sub k represent? And I know what you're thinking right now. Riley, don't say it. This is representing the height of the kth rectangle. And so this is the height of one of the rectangles. That's the function value at the kth rectangle. What does the delta x sub k represent? Well, then that would be the width of the rectangle. Not only it is the width of each rectangle, but it's the width of that rectangle, the kth rectangle there that goes along with the height. And lastly, what will the limit as delta x approaches 0 of r sub n calculate? The moment you've all been waiting for. Here's the payoff. So yes, indeed, if we let delta x, the width of each rectangle, shrink towards 0, there would be more and more rectangles to fill up this space, which means that these jagged edges here, right, where my rectangle does a poor job of approximating the curve on the graph, well, that would become less and less. And so as I increase the number of rectangles, as you did in your activity, I'd finally be left with the exact area underneath the curve. And so that is the limit as delta x approaches 0 of r sub n calculate. That leaves us with the exact area. And that's time for all caps, comma, baby. That'll generate the exact area under the curve. Wonderful. Good work today, ladies and gentlemen. So we've got our OTL number 3 for next time. Thank you for working well, even in my absence, and I hope to see you guys again soon. I'll go ahead and stop the recording and save it now. Thank you. Thank you.